So now, so I was saying, for those of you out there in Zoom, I take it you can see my screen. So what I'm saying is that this question, just ignore it, all right? For the reasons I mentioned. Now you should be able to do number 13, right? But as I said before, in addition, there are some more questions I've provided. And those questions will be located, hold on, wait a minute. How come? I'm sorry, folks, out there in Zoom. I'm messing up today. Okay, now you guys should be able to see the screen. So I was saying, I'm going to say this for the third time. This question, number 12, right? That one you can ignore, all right? The one that you can do, if you have not done it already, is question 13. And as I said before, I'm going to, I've provided some additional questions. So if you go to Canvas, go to Files, and you go to this folder called Additional Kinetic Questions, I've provided two links with more questions. And in fact, I have copies of them here. So for those of you who are here, in fact, I'll give you these now. And for those of you out there in Zoom, you can download and print. And you're going to submit. Oh, wait a minute. Oh, okay. So that's one page. Well, these questions should work out fine. But again, if you have any issues, please feel free to call me. And so that's the first one. The second one is this one right here. So that's 3 additional questions for you to practice on so that you get a good feel for how to do these questions so that by the time the test rolls around, you should be in good shape, all right? Okay, so moving on from that, let's talk about some other topics in kinetics, so chemical kinetics. So what we're going to look at now is basically how do we calculate or derive the relationship between concentration of a reactant and the time, all right? And we're going to obtain or look at what we call integrated rate equations, right? These are not the same thing as the rate laws. These are equations which relate the rate, I'm sorry, not the rate, the concentration of reactant to the time. The rate laws that we were talking about earlier, last time, we were looking at the relationship between the rate and concentration, but now we're going to look at the relationship between concentration and time. And we're going to look at it for 3 types of reactions: 0-order reactions, first-order reactions, and second-order reactions. Because believe it or not, I don't know if I mentioned this last time, but there are some reactions which are 0-order reactions. What that means is that the rate will not be affected by any change in the concentration. And there are some reactions where, in fact, that is the case. So let's talk about 0-order reactions. So we're going to assume that this is the equation, A to form a product or product, right? So we can write down this expression, rate is equal to minus delta A, or change in A, divided by the change in time. And that would be equal to, according to, if it's a 0-order reaction, that rate would be equal to K times the concentration of A raised to the 0. Now, we all know anything that's raised to the 0 is equal to 1, right? So therefore, that means that the rate would be equal to K. So what that tells you is that the rate is just constant. It doesn't change if you change, whoops, I went backwards. It doesn't change if you change the concentration of the reactant, all right? So basically, we can write down an expression like this for K. K is equal to rate divided by the concentration of A raised to the 0, and if you look at this combination here, in terms of the units would be for K, M over S, all right? Now, what we're going to do is look at what happens when we set this expression here be equal to K, because that is equal to the rate, and the rate is equal to K. So I'm going to jump several steps, and the only reason why, because the steps involve calculus, and I don't think most of you have done calculus, right? But basically, if you do what is called an integration of both sides, right? Then you're going to get this expression right here, right? And this expression relates the concentration of A to the time. The concentration of A at a particular time would be equal to the initial concentration of A minus the rate constant K times the time, all right? So that's basically how we get the relationship between the concentration of A and time. Yes, ma'am?
Same title. Sorry.
Oh, yeah. Go over here, get rid of that. That's the title, zero order reaction. Okay, so that's a very important equation in terms of determining K, right? If you want to experimentally determine what K is, then what you could do is, and this is just giving you what the different terms are. So what you could do is recognize that this equation is in the form of Y is equal to C minus MX, right? And if you're familiar with the equation of a straight line, you should recognize that this is an equation of a straight line where the slope is negative, right? So basically what this is saying is that if you plot concentration of A versus T, you're going to have a negative slope straight line, as you can see in this picture, where the slope is equal to minus K. So if you can imagine you did an experiment and you get different values of A and T, you plot A versus T, you're going to get a negative slope, and then you're going to, or a negative slope line, and then you're going to find a slope. That slope value will be equal to minus K. So therefore K, which is the aim of this exercise, will be equal to minus the slope, all right? So that's basically how we can determine the rate constant for a zero order reaction based on the integrated rate equation. Another thing I want to talk about here and introduce to you here is the concept of half-life. Let me get rid of this. Okay, so what is half-life, right? Half-life is the time taken for the concentration of the reactant to decrease to half its initial value, all right? So whatever the concentration is at a particular time, 0, and then it takes some time to get to half that value, then the time taken for that would be the half-life, right? And we can calculate the half-life for a zero order reaction if we set the time T, this time here, we set that to be equal to the half-life, which is T half, and we set that A, the concentration of A, is equal to half the initial concentration of A. So when you plug T half here and this expression here, you're going to get this equation right here, right? T half is equal to the initial concentration of A divided by 2 times the rate constant, all right? So you could be asked that question as well. How do you calculate the half-life? Well, this is the equation that you're going to use to do that. And that is only applicable to a zero order reaction. So basically, these two equations, this one here and this one here, is applicable only to zero order reactions, right? And what we're going to see is that you're going to have different types of equations for integrated and half-life calculations for first order and second order reactions as well. But for now, this is the case for zero order reaction. In fact, let's look at going back to the assignment. Okay, where's the assignment? Okay, so at this juncture, we should now be able to do question number 4, right? So the question says the reaction of reactant A is zero order if the initial, turn on this thing here. If the initial concentration of A is 0.545 and the half-life is 236 seconds, answer the following questions. And the first of which is how much time is required to reduce the initial concentration by 65.5%, right? So what I would do is, this would be the initial concentration, right? So the concentration of A would be reduced by 65.5%. So what does that mean? That means that the concentration of A at that time would be 0.545 M minus 65.5% of M, right? So 60, I'll put 0.655 times 0.545 M. Should be zero here, all right? So where's my calculator? Okay, so I'm gonna work out this part first. So that's 0.655 times 0.545, and that gives 0.357, and then 0.545. So let me do this. So 0.545 minus 0.357. And again, as I always say, please do these calculations along with me because I'm subject to error. I'm only human. Just to keep me on my toe, all right? So that would be the amount of A that is present at the time that the question is asking for. Now, the question says that the half-life is 236 seconds. Now, remember, the equation that we are given for the half-life is equal to the initial concentration of A divided by 2K, right? So therefore, we can find out what K is. K would be equal to concentration of A initial divided by 2 times the half-life, which is equal to, now the concentration of A initial is 0.545 M divided by 2 times, what's the half-life? 236 seconds, right? So that's 0.545 divided by 2 divided by 236. So according to my calculations, K is equal to 1 point, how many sig figs? 3 sig figs. So 1.15 times 10 to the minus 3. And the units of K in this case would be M over S, because we have the M here, we have the S here, right? So let me see. So to get T, well, the equation for A is equal to the initial concentration minus KT. That's what we just saw, right? The aim is to find T. So T would be equal to the initial concentration of A minus concentration of A over the K that we just found. So let's see what that gives. Oh, let me see here. 0.545 M minus 0.188 M divided by K, which is 1.15 times 10 to the minus 3 M over S. And whatever that gives, that will be the answer. So let's see what that gives. 0.545 minus 0.188 equals that divided by 1.15 times 10 to the minus 3. And according to my calculations, rounded off to 3 sig figs, the answer is going to be 310. And the units, these will cancel out, would be seconds. Should be a decimal point here to make that 3 sig figs. All right? And that's basically how that is done. All right? Any questions about this? Any questions? Any questions? Oh, I'm sorry, yes, sir.
For the last equation, would that be just?
This here?
Yeah, would that just be A initial minus A?
Right, A initial minus concentration of A divided by K. And that comes from what I did up here.
Okay.
I just rearranged that
Okay.
equation. Right. Okay, yes, ma'am.
310 with an S.
3 times, right, 310 with a decimal point seconds. Yeah. Okay, any other questions? Any other questions? Any other questions? All right, so, I guess it's okay for me to clear this, right? Or are you still writing? Yeah? Okay, going back to the PowerPoint, let's talk about first order reactions. Now, in the case of first order reactions, in that case, the rate law would be this. Rate is equal to K times the concentration of A raised to the power of 1, all right? So basically, again, because rate is also equal to minus the change in concentration of A over change in time, we can, well, firstly, let's look at the units. For K, that would be rate, well, if we rearrange this equation here, we're going to get K equal to rate divided by concentration of A. Now, the units of rate would be M over S, or it could be M over any unit of time. It could be hours, could be minutes. We're just using seconds here. If that's the case, M over S divided by M would give you ultimately 1 over S, or S to the minus 1. So basically, the units of K for a first order reaction must be some unit of time raised to the minus 1. It could be seconds to the minus 1, hours to the minus 1, days to the minus 1, years to the minus 1, all depending on how fast a reaction we're talking about, all right? Now, we're going to set again, like we did before, in the case of the first zero order reaction, we're going to set this term here, this time equals to Ka. And again, I'm going to skip some steps because again, calculus is involved. And ultimately, you're going to get this equation right here. In fact, there are 2 forms of the equation. You have this form of the equation here, where the concentration of A is equal to the initial concentration of A multiplied by E. I don't know if you're familiar with that constant. I don't remember what its value is. Raised to the minus KT. And then there's this form, which is actually more useful, all right? This form is useful when you're doing calculations of certain types, but this is more experimentally useful, right? So basically, this is the equation. You can use this or this, depending on what the question is asking for, to represent the relationship between the concentration and time for a first order reaction. If you recall, I mentioned half-life before in regards to zero order reactions. We have to talk about that also with respect to first order reaction. So just to remind you, the half-life is the time taken for the concentration of a reactant to fall to half its original concentration, right? So again, we're going to set T is equal to T half, which is a half-life, and concentration of A is equal to the initial concentration of A divided by 2. So when you plug those values into the equation I showed you, you're going to get this expression right here. T half is equal to ln, the concentration of A, divided by the concentration of A initial divided by 2, and all of that divided by K. Now, of course, we can cancel out these initial concentration of A terms, and this simplifies to this expression right here. Half-life is equal to ln2 over K, which is also equal to 0.693. If you punch ln2 into your calculator, you're going to get 0.693 and some other digits, right? Now, one unique thing about this particular half-life equation, especially when compared to the zero order, and we're going to see compared to the second order equation, is that this equation has no concentration terms in it, right? So what that tells us is that the half-life is not dependent on the current concentration of your reactant, right? So basically that doesn't come into play when it comes to calculating the half-life. That is not true for the zero order reaction, and you're going to see it's not going to be true either for the second order reaction, right? Basically, because K is a constant and Ln2 is a constant, then the half-life of the reaction is going to be constant, right? So here's a question it's asking, what is the half-life of N2O5 if it decomposes with a rate constant of 5.7 times 10 to the minus 4 seconds to the minus 1? So this begs the question, and this is a question that you have to ask yourself when you're given a question like this. What type of reaction is it? Is it first order, second order, or zero order, all right? And I can easily tell that this is a first order reaction. Why? Because of the units of the rate constant K. the unit of K is seconds to the minus one. As I said before, the unit of K has to be some unit to the minus one of time, all right? So basically that tells me that I need to be using this equation here to calculate the half-life. So I think I have it here already. So the half-life is equal to ln2 divided by K. All I have to do is put where K is 5.7 times 10 to the minus 4 seconds to the minus 1, and then do your magic on your calculator, and that would be the answer, 1200 seconds, which is the same as 20 minutes. And that's it. That's how you solve that problem. Okay, any questions about this one? Excuse me. Any questions? Any questions? Okay, so this is the question, how do I know it's first order? I just said it, right? Because of the unit of time, or unit of K being time to the minus one. Okay, I think, okay, I think I'm missing a slide. Hold on, let me check something. Oh. All right, it's kind of out of order. And there's one graph that's missing. Shoot. Okay, let me move this up here. Okay, so let's talk about some graphical representations of the first order reaction, right? So basically what you'll find, and this is based on the equation, let me see if I can squeeze up here. Concentration of A is equal to the initial concentration of A times e to the minus kt, right? So what this graph is showing you is what happens for a first order reaction when you plot concentration of A on the y-axis versus time on x-axis. And you see a curve here. And if, again, this is something from your math courses. If you are familiar with this particular constant here, if you raise it to minus kt or minus anything, then you'd expect to see a curve looking like this, right? With a decreasing slope approaching the x-axis but not touching it, right? It will come closer and closer and closer and closer, but not actually touching the x-axis, right? And here you can see the half-life phenomenon that I was mentioning before. Remember I said that the half-life of first order reaction is constant, doesn't change, right? So basically you're starting with initial value of A for the concentration of A. And after one half-life, right, the concentration is reduced from the initial value of A0 to A0/2. And then for another half-life, from A0/2 to A0/4, right? So that's another half reduction right there. And it just continues until, again, infinity, basically. But basically with each half-life, the concentration of A is reduced by half, all right? So basically, if you're talking about one half-life passing by, then basically the end value here, because this is concentration of A is equal to initial concentration of A divided by 2. This end value here is going to be 2, which means that the concentration of A would be half of A0. If two half-lives pass by, then the concentration of A would be equal to a quarter that value of the initial concentration of A. If the number of half-life passing by is 3, then basically N is equal to 8, and so on and so forth. If this is 4, then N will be equal to 16. So basically, we see here that for each half-life, how should I write this? The concentration of A will be equal to the concentration of A initial over 2 n. Over half n, I'm sorry, half n. Or I should say multiply by half n. What am I saying? So I'm just going to squeeze this right here. Half n, all right? So that's another way of stating the relationship between the concentration of A and A initial, where n is equal to the number of half-lives. Number of half-lives. Okay? So that's the relationship between the concentration of A and the initial concentration of A. Okay, now another consequence of this equation here is seen when you arrange, and this is a graphical consequence, I should mention, is when you arrange the equation to get a more linear expression. So let me show you how that is done. And let me squeeze that down here. So remember now, I said another way of expressing this equation is ln A is equal to ln, the initial concentration of A, minus KT, right? So if you look at this equation carefully, you see it's also an equation of a straight line where this is equal to y, this would be the intercept C, and this would be the slope. Oops. M, and this would be the x value, right? So basically, if you plot the natural log of the concentration versus time, you're going to get a straight line when you plot it. And this is what is demonstrated here in this actual real example where the reaction is this represented by this equation right here, right? If you plot the natural log of the concentration of N2O5, which is the only reactant, versus time, you're going to get a straight line with a negative slope, and that negative slope would be equal to minus K, the rate constant, all right? And we all know how to get the slope. It's rise over run. And basically, if you do that for this particular reaction, based on this data, then you'll be able to get the slope. In fact, let me see if we can do that. The slope here would be equal to 21.50 second, no, not seconds, oh, that has no unit, minus 20.34 divided by 2430 seconds minus 400 seconds, right? So let's see what that gives. The numerator 21.50 minus 20.34 equals, okay, so I got okay, so I got 1.16. And the 2430 minus 400, I got 2030. Now, the reason why I hesitate, because the value should be negative. So I think these two should be switched, right? So this should be negative. So 1.16 divided by 2030. And according to my calculation, this gives minus 5.71 times 10 to the minus 4. And so basically K, this should be minus. So therefore K is equal to 5.71 times 10 to the minus 4. And the units here would be seconds to the minus 1. Again, because it's a first order here. All right, so that's basically the graphical representation of the relationship between another graphical relationship, I should say, between the concentration of a reactant and time for a first order reaction. Okay, let me see, any questions about this? Any questions? Okay, so here's an example. It says the reaction, and it gives you the equation, is first ordered in A with the rate constant of 2.8 times 10 to the minus 2 seconds to the minus 1 at 80 degrees. How long will it take for A to decrease from 0.88 to 0.14 M, all right? So of course, the first thing that comes to mind is either one of the two forms of the equation for the first order reaction. Now, this form is the one that will be most useful because this is where you're going to isolate T, right? The question gives you the initial concentration of A, it gives you the current concentration of A, and it gives you the rate constant, so this is K, right? So basically, you have to rearrange this equation to solve for T. So that's what T is equal to. T is equal to the natural log of A initial minus the natural log of A divided by K. And then you put the numbers in, right? And you're going to end up with your time that the question is asking for. How long will it take for the concentration to decrease to that level? That would be equal to 66 seconds. All right, so that's basically how you do that. And, based on what we have just done, I'm going to leave you to do number 5 in your assignment. Let me see here, number 5. Yes, number 5. So in your assignment, number 5 is basically questions dealing with first order reactions. Again, if you have any problems, please feel free to contact me. But I think you should be able to do number 5, which is on page 4 in your assignment. All right? Okay, any questions about this particular example? Any questions? Any questions? Any questions? All right, moving along. Let's move on now to a second. Oh, sorry. You want to? Oh, go ahead. Okay, so let's talk about second order reaction, right? Same approach we're going to take, but the equation will be different. Again, we're assuming that rate is equal to the minus changing concentration of reactant over time. And in the case of a second order reaction, that rate will be equal to K times the concentration of A raised to the second power because it's a second order reaction. So we said this equal to that. First we have to find the units, I'm sorry. So as far as the units are concerned, the units of K would be equal to the unit of rate divided by the unit of concentration squared. So this simplifies to 1 over ms. Or another way of stating this is m to the minus 1, s to the minus 1, same thing, all right? And again, the unit of time doesn't have to be seconds, it could be hours, minutes, and so on, right? So we set this expression equals to that expression, and again, several steps will be skipped because those are calculus steps. So ultimately, this is the equation you're going to end up with, all right? 1 over the concentration of A is equal to 1 over the initial concentration of A plus KT, all right? So this is the equation. Again, if you look at this carefully, you'll see that this is in the form of an equation of a straight line where 1 over A would be Y, 1 over the initial concentration of A would be the intercept, and KT, or K I should say, would be the slope, right? Or the gradient, all right? And T would be X, I'm sorry, T would be X, all right? So the slope is M, so that's Y is equal to C plus MX, straight line equation. And I think I have, I don't have, here's a plot. So if you plot based on, the data, 1 over A over time, you're going to get a straight line where the slope is equal to K, and the intercept on the y-axis is 1 over the initial concentration of A, because when T is equal to 0, then you're going to get 1 over A is equal to 1 over the initial concentration of A, all right? Half-life, we talked about half-life again, it applies here in this case. Half-life is where T is equal to T half, which means that the concentration of A at that time would be equal to the initial concentration of A over 2. If you were to plug this where A is, and T half where T is, you're going to get this equation for the half-life. The half-life is equal to 1 over K times the initial concentration of A, right? So that's basically the half-life. It's dependent on the concentration of A, which is, again, as I said before, not true in the case of the first order reaction, all right? Okay, so that's basically all that we have to say about the second order reaction. So just to summarize, for zero order reaction, the rate law is rate is equal to K, and the equation which relates the concentration to time is concentration of A is equal to the initial concentration of A minus KT, and the half-life equation is what you see here. Half-life is equal to the initial concentration of A over 2K. When the order is 1, then the rate is equal to K times concentration of A. The equation which relates, well, there are two equations I showed you, both basically different ways of saying the same thing, but this is one of them. ln A is equal to ln the initial concentration of A minus KT, and the half-life will be equal to ln 2 over K, and then 2, the order being 2, rate will be equal to K A squared, and the rate law is 1 over the concentration of A equals to 1 over the initial concentration of A plus KT, and the half-life for that is this equation right here, T half is equal to 1 over K times the initial concentration of A, all right? So basically, these are the only orders that you have to be concerned with, 0, 1, and 2, and the equations, the related equations, and the half-life expressions, all right? Okay, so with that said, let me get out of this here. Oh, wait. You guys finished with this? All right, so let me get to the PowerPoint because I don't have any examples on the PowerPoint slide. So let me get to the assignment actually. And we're looking for specifically. Okay, so this is the question that you guys need to do on your own. And then let's move on to question number 6. So the question number 6 gives you the rate law. So that tells you, this is the equation, and they gave you the rate law. So, and they gave you the K value, right? So basically, because the concentration of the reactant I is raised to the second power, it's a second order reaction, right? Okay, so the first question is asking, what are the proper units of K, right? Well, we did that earlier, because if you look at this equation here, we can say that K is equal to rate divided by concentration of I squared, right? Now, assuming that the rate is given in M over S, which they didn't tell you, they probably should have told us that. I'm just going to assume that the rate unit is M over S divided by I squared, so that would be M squared in terms of units. Then basically the answer is M to the minus 1, S to the minus 1, all right? So that's the answer for the A part. Now, the B part is asking for you to calculate the concentration of I if the concentration of I minus initially is 0.40 M. Now, if you recall, the equation for that is 1 over the concentration of I is equal to, yes, ma'am.
S, to have that -1 up by there, wouldn't we have M2 squared times S squared?
I'm sorry?
Like, wouldn't we have, instead of M over S over N squared, wouldn't we have M over S
No, because
over?
this M cancels out with one of these. Remember, there's a two here, right? So basically, you're going to have this. 1 over S divided by M, right? Well, that would be the same thing as this.
Okay.
Because 1 over M is
Okay,
M to the minus 1.
okay,
And 1 over S is S to the minus 1, right? Okay, so as I was saying, the equation for the second order reaction is 1 over the concentration of, in this case, I, is equal to 1 over the initial concentration of I, plus KT, right? Now, what the question is asking for is T. So therefore, T would be equal to 1 over the initial concentration, 1 over the concentration of I, minus 1 over the initial concentration of I, all over K. And we put the numbers in. Oh, my bad. We don't need to do this. We just need this because the question gives us the initial concentration, the time, and it's asking for the concentration of I. So let me just go from there. So 1 over the concentration of I is equal to 1 over 0.40 m plus K. Now K is given as 7.09 times 10 to the 9, and the units would be m to the minus 1, s to the minus 1, multiplied by the time. What's the time? The time is 2.5 times 10 to the minus 7 seconds, all right? So let's see. Let's work out this part first. So 7.09 times 10 to the 9 times 2.5 times 10 to the minus 3. And, oh, minus 7, I made a mistake. Okay, do this again. 7.09 times 10 to the 9 times 2.5 times 10 to the minus 7. Okay, so according to my calculation, this works out to be equal to, let me see here, how many sig figs? That's 3, that's, oh, where did I get this from? Okay, let me do this again, I'm sorry, folks. 7 times 10 to the 9 multiplied by 2.5 times 10 to the minus 3. Okay, 10 to the minus 7, okay. So, okay, so this is what I got. Run it off to 2 sig figs, 1800, and the units here would be m to the minus 1, right? And to that, I'm going to add 1 over 0.4. So 0.4, 1 over that is equal to 2.5 m to the minus 1, right? So what does that give? 2.5 plus 1800. I got 180. 1082.5 m to the minus 1. So 1 over the concentration of I, or I should say concentration of I, is equal to 1 over 1802.5 m to the minus 1. And the answer I got is 5.548 times 10 to the minus 4. Yeah. Actually, you know what? I forgot to round off. So this will still be equal to 1800, right? So let me leave that as 1800 and m to the minus 1. And therefore, 1 over 1800 is going to be the final answer, whatever that gives. So concentration of I would be 1 over 1800 m to the minus 1. And let's see here, 1800. Okay, so 5.6 times 10 to the minus 4 M would be the answer. Right? So that's basically how that is done. Yes, ma'am. 1 over 0.4.
1 over 0.4?
Yeah.
But
0.4.
So are you, Professor, so do you not add the 2.5 to the 1800? I'm confused.
Right, yeah, you do add the 2.5 to the 1800, but you're going to get a number which you have to round off to the correct number of sig figs, or in this case, decimal places. Right? So basically, you have to round off to where the 100th place is right here. When you're adding 1800 to 2.5, you're adding 1800 to 2.5, right? You're going to get 1802.5 on your calculator. But because this is the highest place significant figure here, when you're adding, you have to round off to that level here. So therefore, the answer is going to be 1800 still. All right? And then you do the rest. Okay, any other questions about this? Any other questions? All right, let me, is it okay for me to clear this? All right, let me clear this. Let me do this. Let me go back to the PowerPoint. And okay, so now we're going to get to, and I think this is out of order again. Yeah, got it. Okay, let me bring this down. Here, okay. All right, so let's talk about the collision theory. All right, so we can use our imagination to think of what will happen when you have two molecules coming together and reacting to form products, right? Obviously, they must have a certain amount of energy so that when they collide, then you have changes taking place where bond breaking will occur, and then the subsequent bond formation will result in products being formed, right? So the theory that is used to explain this is called the collision theory, right? And basically, what the theory says is pretty much what I just said a while ago, right? Atoms, molecules, or ions must collide with each other. But the thing about it is that not all collisions will be successful in terms of forming products, right? So the question now becomes, what's the difference between a successful collision and those collisions that are not successful? And the answer is that the molecules must have a minimum amount of energy which is required to cause a reaction to take place. So basically, if the molecules collide and don't have that energy, they'll just bounce off each other, right? But if the molecules have sufficient energy, then when they collide, it results in a chemical reaction taking place, right? So this graph here basically shows you the, on the x-axis, you have the fraction of molecules that contain a certain amount of kinetic energy, and the x-axis is kinetic energy. Now I want us to focus on the blue line for the time being, right? The blue curve, right? This is temperature 1, right? Which is a lower temperature compared to temperature 2. So for temperature 1, this is the plot right here, right? Now let's say that the amount of energy needed for the molecules to react is represented by this part right here. Then to calculate the number of molecules or the fraction of molecules that would have that energy, that would be the area under that curve, all right? Now, if the temperature increases from T1 to T2, this would be the curve right here, right? And again, if you want to determine the fraction of molecules that will have enough energy to cause the reaction to take place, you take not only the area here, which is blue shaded for T1, but you have to include this pink shaded area as well. So this entire area here would represent the fraction of molecules that will have at least that minimum energy to cause the reaction, right? So basically what this graph demonstrates is that as you increase the temperature, basically the number of molecules that has enough energy to cause a reaction would increase, all right? So that's basically the consequence of the collision theory. So that energy that I just referred to, the minimal energy needed, right, for molecules when they collide to react, that's called the activation energy, represented by EA, right? So basically what EA represents is the minimum energy that the colliding molecules must have in order for a successful reaction to take place. And there are a couple of things that would affect whether or not that would take place. And for, again, I don't know if I mentioned this before, some of what you're going to learn here is important in organic chemistry, because one important reaction that you're going to learn in organic chemistry is what they call the SN2 reaction. I won't tell you what that means, but basically it's a reaction in this case between this molecule, which is known as bromomethane, and the iodide ion, right? Now, if you think about it, well, let me just say this first. In this case, the carbon atom is bonded to the bromine atom, and bromine being more electronegative will have a partial negative charge, while the carbon will have a partial positive charge, right? The iodide will have a negative charge, right? So if you think about the iodide ion approaching the bromine directly, nothing much will happen, because negative, negative, you know what happens, right? They repel each other, right? But in this case where this is negative, this has a partial plus charge, whoops. This is a partial plus charge. This is a partial negative, partial negative charge. So basically what's going to happen here is that the negative iodide ion will be attracted to the positive carbon atom. And therefore a reaction will take place, because what will happen is that the iodide will donate a pair of electrons here. The result will be the bond here being broken, and you're going to have the formation of a new product. So the point I'm getting at is that when the molecules are colliding, spatial orientation is important, right? Relative to each other. And that can be clearly seen in this particular example. And you're going to explore this in a lot more detail. For those of you who have to do organic chemistry, you're going to see that you need to understand and have a good feel for the three-dimensional shapes of molecules in order to see, okay, how will this react? Where will the attacking molecule attack? Will it attack something positive or negative? And what will be the products? And also, what will be the three-dimensional shapes of the products? So those are things that you're going to learn about in organic chemistry, all right? One important aspect of the collision theory is, well, this is not, it's kind of related, let's put it that way. We call this a transition state theory. And basically what this theory says is that at the point where you have bond breaking and bond making taking place at the same time, you have a structure which is known as a transition state, all right? So the example that is used here is a reaction between carbon monoxide plus NO2 to form carbon dioxide and NO. That's the equation here, right? So basically, just looking at the equation, there's obviously a transfer of oxygen from the NO2 to the carbon monoxide to form the products, right? So therefore, there must be some bond breaking taking place here between the nitrogen and the oxygen, and bond formation here between the carbon and the oxygen. So that's what this diagram is representing. Here we have the carbon monoxide, here we have the nitrogen dioxide, right? So therefore, there's going to be a transfer of the oxygen from the carbon, from the nitrogen to the carbon. So you're going to have bond formation here, and at the same time, you're going to have bond breaking here. So here, this kind of shaded line or dotted line basically represents a bond being formed here, and this represents a bond being broken here simultaneously, right? So we call this species a transition state. And the reason why it's called a transition state is because its existence is transient or fleeting, right? As soon as it forms, it disappears, right? And I think for the first time in history, a couple of years ago, somebody actually isolated the transition state of a reaction, because before then, nobody could isolate the transition state of any reaction, right? We can only infer the structure based on the structure of the reactants and the structure of the products. We can say, okay, well, the transition state must look like this, but somebody actually succeeded in doing that for a particular reaction, which which is a very interesting feat. So after the transition state is arrived at, then this bond here, which is being formed, will be fully formed, and this bond that is being broken will be fully broken, and you're going to end up with your product, right? So basically, that's how the transition state theory works. Some things I want to point out here. This is a plot of energy versus the progress of the reaction, right? So the activation energy for this reaction would be represented by the difference between the energy of the reactants and the energy of the transition state, right? And in this case, the activation energy for the forward reaction is 134 kilojoules, right? And then the difference in energy between the reactants here and the products here would simply be the enthalpy of the reaction. And that is something you should have met already in general chemistry too. As you can see here, the energy of the products here would be lower than the energy of the reactants, so therefore delta H here, the enthalpy of the reaction will be negative, all right? Also, you can have the reaction going in reverse, right? Now, if the reaction is going in reverse, for one, delta H will be positive, right? Because you should have learned in Chem 1 that if delta H is positive for the forward reaction, for the reverse reaction, it's negative. And also, in this case, for the reverse reaction, the activation energy will be the difference between the energy of the products here and the energy of the transition state. So in this case, that activation energy will be equal to 360 kilojoules, all right? So that's basically the transition state theory. Okay, any questions about this? Any questions? Okay, so, another term that is used for transition state is called the activated complex, or the activated complex. There's another term in organic chemistry, but I won't go into that. So whenever you see the term activated complex, it's the same thing as a transition state. Okay, so I spoke about the enthalpy of the reaction. Okay, now let's look at the effect of temperature on rates experimentally. We talked about the fact that the temperature would increase the rate of the reaction, and I showed you that in the graph 2 slides ago. Well, this guy, Arrhenius, who you should have met before in your general chemistry, he came up with his definition of acids and bases. He did a lot of work in chemistry in different areas. And he proposed this equation here, which shows you the relationship between the rate constant for a reaction and the temperature, right? And as you can see, there are several terms in this equation. You have K, which is a rate constant. You have A, which is called the frequency factor. I'm sorry. You have EA, which is the activation energy, which we just talked about. R is a molar gas constant, and in this case, R is equal to 8.31 joules per mole Kelvin. All right. So not the other R value that you would probably be more familiar with. All right. And then T would be the temperature in Kelvin. All right. So that's the equation relating the rate constant to the temperature. All right. So, these are the terms here, right? So EA is the activation energy. R is the molar gas constant. T is the temperature in Kelvin, and A is the frequency factor. Now, the frequency factor is basically, how should I explain it? It takes into account two terms. It takes into account how frequently the molecules will collide with each other, and also the orientation of the molecules, which we talked about earlier. But before we get to that in more detail, so this is the equation that Arrhenius came up with. We can have another form of the equation. If you find a natural log of both sides, you're going to end up with this expression right here. And this is more useful graphically and experimentally because, as you can see here again, this is the form of a straight line with a negative slope, where ln k would be the y value, 1 over t would be the x value, and ln a would be the y-intercept, and minus, or EA over R, or I should say minus EA over R, would be the m value, which would be the slope, right? So basically, if you carry out an experiment where you plot ln k versus 1 over t on the x-axis, you're going to get a straight line where the slope is equal to minus EA over R, and you can use this to calculate activation energy, EA, because once you get this, then you simply do slope EA is equal to minus slope times the molar gas constant, right? So that's how you can calculate the activation energy of a reaction based on this kind of data, all right? Okay, so that's basically showing you the relationship between the rate constant and temperature, right? So basically what that means is that as the temperature increases, the rate constant increases, and if the rate constant increases, then the rate of the reaction increases, right? Okay, any questions about this? Any questions? Okay, so this is just an explanation of the frequency factor. It's a product of two terms. One is the collision frequency, and the other one is a probability factor, which takes into account orientation, basically, required for the molecule to, or molecules to react when they collide, all right? And then this part of the Arrhenius equation basically represents a fraction of molecular collision sufficiently energetic to produce a reaction. So that's what this part means of the Arrhenius equation. Okay, so this is just showing you the difference between an exothermic and endothermic reaction, taking into account the role or the part that transition states play in these kinds of reactions. By the way, what time is it? Oh, okay. 10 more minutes. So in this case, we have the exothermic reaction. We know it's an exothermic reaction because the energy of the products is less than the energy of the reactants. And this is the activation energy, the difference between the energy of the reactants and the transition state. And then this is for the endothermic reaction, where the energy of the products would be greater than the energy of the reactants. And this would be the activation energy again, which is the difference in energy between the reactants and the products. I'm sorry, the transition state. All right. So again, that's the definition of the activation energy. It's the minimum amount of energy required for the reaction to take place. If the molecules don't have that activation energy, then basically the molecules will not react to form products. All right. Okay. So I'm not sure if we'll be able to finish this question in time, but I can at least give you guys a start. Question number 7, I think it is. Let's see here in your assignment. Oh shoot, I didn't finish question number 6. Oh my God, okay, I'm sorry about that. Okay, okay, let's look at C. So we're still dealing with a second order reaction. In the case of C, it says if the initial concentration of I is 0.40, calculate the half-life. Well, to remind you, the equation for the half-life for a second order reaction is half-life is equal to 1 over K times the initial concentration of A, right? So basically it's 1 over K. What's K again? What was K? K is 7.0. So (7.0) times 10 to the 9, m to the minus 1, s to the minus 1, right? Multiplied by the initial concentration, which is 0.40 m. And let's see what that gives. 7 times 10 to the 9 times 0.4, and then 1 over that. So according to my calculation, this works out to be equal to 3.5. How many sig figs? 2 sig figs. So actually 3.6. 3.6 times 10 to the minus 10 seconds, because this is going to cancel over that. All right. Okay. So that's the C part. Any questions about it? Any questions?
Write that in like the A part?
Yeah, I just scrolled up because I wanted to see what K was. Yeah, I'm sorry. Let me scroll back down here. So, whoops. So this is the answer for the C part, right? Okay, now for the D part, it says, if the initial concentration of I is 0.80 m, how much time will it take for 75% of the iodine atoms to react? So if 75% of the iodine atoms react, that means that 25% of the iodine atoms remain, right? So first thing I'm going to calculate here is how much remains, right? So that would be the concentration of iodine at that time would be equal to 0.25 times 0.80 m. So that's a quarter of 0.8, which would be 0.20 m, right? So the equation for calculating, relating the concentration to time is this, plus kT, right? We need to find T, so therefore T is equal to 1 over concentration of I minus 1 over the initial concentration of I divided by K. So that would be 1 over 0.20 m minus 1 over 0.80 m divided by K, which was 7.0 times 10 to the 9, m minus 1, s to the minus 1. And let's see what that gives. 2 minus 0.8. And then I divide that by 7 times 10 to the 9. So according to my calculations, I got 5.6 so 5.4 times 10 to the minus 10, and the units here would be seconds. And that's how that is done. Any questions about this one? Questions? Okay, is there any more questions after this? For D? Oh, no, okay, good. I think I'm gonna stop here, but before I let you guys go, let me make sure I get everybody's attendance. And let me remind you also about the event on Wednesday of next week concerning STEM careers. So please come and attend. I probably should be giving you extra credit for, maybe I'll do that. Okay, is Gilcrease here?
Yes.
Okay. Gilcrease is here. Let me see, is Lucky here? Let me see.
Yes, I'm here.
Oh, Lucky's here, okay. Renfro is here. And Salvador. Salvador, okay. All right, so that's it, folks. So I see you guys on Wednesday. Sit down. Building 3 in the common area. You know that area right here. Hmm? Yeah. Everybody got a copy of each of these? Okay.
You said the common room, is it like a separate room?
No, you know that area where the cafeteria is? Right, that area. Sometimes they have meetings there and they have seats set up. If you enter through the back part here, basically you're entering from the front part of where the presentation will be.
Because,
Why?
and this is the 29th, right?
This is the fifth.
Oh, the fifth, okay, good, good,
Yeah.
okay, that's fine. Yeah, because we have an event, this Wednesday, they're gonna use the same area, so I was,
Oh, okay,
that's fine.
yes. I made sure, call, Marjorie and ask her what dates are available. She
Yeah,
said
yeah,
that, she said that the fifth was, she said the fifth of February and the fifth of March, so I just chose the
Perfect.
earlier date.
That's great. All right, thank you, have a good one.
You too.